Hi everyone. I'm going to try to record a short video because you hit 50%. Okay, so basically for the CHEM242 final exam, it's similar in format to the midterm. I think, I don't know, let me just double check how much time you guys are given. So you can see here, it's from experiments 4, 5, 6, 7, 8. So it's the other latter half of the semester. As you can see here, this is the final exam study guide. Okay, cool. I'm sharing the right thing. So you can see general information. So you just need to know the reduction of the Nylon acetate. It's kind of weird that it's not the synthesis as well, but it's purification, but you're reducing it, which means you're using the NaBH4. The synthesis of nylon 6,6, which was the reaction where you did the polymer. It should also say probably the backlight lab, so you might want to think about that. Synthesis of shell cone. That is a Michael addition. I'm sorry, not Michael addition. That is the aldol condensation. And then I jumped ahead too far. The Robinson annuation is the Michael addition followed by an aldol. And that gives you the Robinson mechanism. And Robinson annuation will always form a 6-membered ring. So hopefully that helps. It says keep in mind readings for lab, blah blah blah. Yeah. So you should have read through the lab manual, looked at the videos. I wouldn't do that for studying, but like I assume that you read through the lab manual throughout the semester. Probably annotations are good having it next to you maybe. Relevant information. I would even copy down the experiment. I would copy down the reagent table, like from your lab report, have that next to you, have the basic mechanisms next to you, since this is, I think, open note because it's online, and also have the reaction, like what type of reaction it is, what functional groups are reacting. This is something you want to keep in mind. It says calculations, mechanisms, rule of reagents. Why do you use what do you use? This is kind of like this is a big one. Acidic versus basic conditions. You need to pay attention. So I think sometimes I even miss that. So right here, like if you see something like H3O+, H+, like sulfuric is a very common one. Sulfuric acid, hydrochloric acid, maybe HNO3, like nitric acid. I don't think you use nitric acid, but like maybe like what's this? Bromic acid, hydroiodic, these are all strong acids. These just mean acidic conditions, and whenever you're in acidic conditions, you have positive or you have neutral. So your base will always be neutral, and your acid will always be positive. As for basic conditions, you might see it like, oh yeah, there's an NaOH. This is the most common one. I haven't really seen anything else. Maybe just an OH minus water. Usually water is just a solvent. You might see that water here too. Like that's hydronium. Just maybe water there as well. I'm not going to draw it for everything. What else is a base? I doubt you're going to see amines here, but maybe NH3 ammonia as a base. KOH could be maybe potassium hydroxide. I can't think of any other really. I haven't really seen lithium hydroxide, so I don't think that's a thing, but maybe these two. Usually you'll probably see sodium hydroxide as a base. So I think that helps. Oh, and in basic conditions, your acid is neutral and your base is negative. So this is something you should realize. Like, so I should never, ever see, you should never see positive charges in basic conditions. And you should never see negative charges in acidic conditions. So hopefully this helps you. Says why do you add, what do you add when you add it, what does it do? So like the role of reagents, like, so some of the reagents actually react, and then some of them are catalytic. I think your base was catalytic in the lab. I can't remember off the top of my head. I think it was your Robinson. Probably was. Just cannot remember things off the top of my head. Once again. Yes, your Robinson annuation had a sodium hydroxide was catalytic. Okay, so then basically you can have catalysts, you can have bases, acids, solvents, like things like that. Limiting reagent, things like equivalents, that's something you should remember from your tables. Reagent tables, the generality of the reactions you did if you were doing blah blah blah. Okay, so this is just basically saying you just need to know you need to know your functional groups. Ooh, what is going on? Don't know if the recording stopped. Sorry, my internet just kind of crashed. I don't think so. So sorry about that. But you need to know the generality of the reactions you did. If you were to do the reaction using other similar molecules, what products would you get? So this is just a question of functional groups. I honestly advise you to even just make up problems with functional groups. So, you know, like if you have an ester, oh, let's make this more complicated. Just add like, oh, let's make a benzene ring. Let's make something like, that's not even a benzene ring. This is horrible, sorry. So maybe I'll just make something a little crazy and, you know, all that. Like, so I would just recommend like noticing that you can make crazy and big molecules just to scare you. Because I got scared when I took the class as well. Okay, so then you also see product analysis. So you got white oil, solid, or an oil. How do you know that product? Okay, so this is basically, you use things like TLC to determine the purity. You know IR. IR, infrared spectroscopy, can tell you what the functional groups are in your product. So if your carbonyl is supposed to react and like you get alcohol, then like you should be able to tell. So those are like different methods, and TLC will help you determine your success of your reaction and your purity of the product. You should be familiar with the following functional groups and their pKa values: alkanes, amines. Another small thing is like H2. H2, so when you have like Al, the height H minus, what is it called? Hydrides. If you have hydride sources, you know, the pKa of that is also around this. So I think it's like H2 is around 60 or something. That's very basic. Amines, terminal alkynes, acetoines, that's 25, ketones, 20. Oh, the alpha proton of the ketones, that's important. And if you're between two, another thing to note, small thing, is if you're between two ketones, this is not anhydride. Remember, anhydride has oxygen in between. So that's not anhydride, but basically this pK is around 10. Like, he's not going to ask you about that specifically probably, but I mean, it's okay to know, because you need to, this could be more of like a conceptual question if you're thinking about acidity, like what contributes to acidity, what doesn't, especially for like alpha carbon, because the alpha proton is so acidic, and then there are other factors that can play a role, like resonance or like inductive effect. I think that's why you learn that you can do, I think, my orgo knowledge is like a little rusty, but where you make a good leaving group, I think you make CH3 into like a 3 bromines or something and you kick it off. Basically, like there can be inductive effects from that. Phenyl is benzene ring with an OH on it. Ammonium, NH3, NH4, carboxylic acid is around 4 to 5, I guess, given here. Hydronium, peroxygenated alcohols. Yeah, it's pretty acidic, but it's not the most acidic thing ever. This is like hydrohalogenic acid. It's just HCl, HBr, HI. Yeah, hopefully that helps. Okay, so then Nmr Ir and Tlc. This is for structure determination. So you need to know how to do this. I think there's mass spec too, but I guess it's not written on here. Maybe it's not focused. I don't know. But I would just also focus on this. Don't forget about it. NMR is nuclear resonance spectroscopy, and you can determine number of unique carbons or hydrogens. And I would really encourage you to do, if you see something like this, when you see like a spectra, I know I'm drawing this badly, but ignore the solvent peak, and if you see something really tiny, like later on around 200, 150, you know, here you may see things that are very tiny, like it could look really tiny, you need to zoom in. These are quaternary carbons. They don't have so quaternary carbons are pretty nice to identify as a tip because they don't have no H's hanging off. And if they don't have any H's hanging off, then there's something easy to determine. As you can see here, like you can also think of chemical shifts. So something like a quaternary carbon like this, that might show, you know, like 150 to 200 range because this is a ketone. So it's going to show in that range. You need to know basic chemical shifts. But if you see something like a quaternary carbon here, and these are all alkanes, they might be around like 20, you know, around 50, 0 to 50 range, and you see tiny quaternary carbon there, that means that you have, you'll have like, yeah, so that'll probably be like a quaternary carbon center right here. So just knowing those, IDing those, like this is like one of my biggest tips. Then another thing you can look at in NMR is like the, what is it called, multiplicities, because then you can see how many neighbors you have, especially when you, like, sometimes there might be tricky questions. So like if you think of this, like you need to realize that like this is methoxy, maybe like OCH3, then this is quaternary down here, and you know this is probably going to be pretty electronegative, not in the 200 maybe region, but you'll see 3 oxygens around this, so that causes the chemical shift to go up. Things like ester and ethers are really and alcohols, esters, like these are like bring the chemical shift leftwards, so it goes downfield. And I would say esters around like 3 to like 4, you know, but if there's multiple of them, it might even shift up to 4 to 5. Yeah, so you just need to realize, look at the number of these electron withdrawing groups that are next to your like whatever carbon or hydrogen in question. I'm sorry, this is like if this was an H, let's say that, then it's not quaternary, but like I know this is a little messy, but just you need to know multiplicities, number. So these are something you can look at easily. I'm not spelling this right. Just don't sit there trying to figure out what multiplet is. Another big hint with NMR, when you have benzene rings, mono-substituted benzene rings will look like usually like a mess, and their integration will be 5H because there's 5 protons on here. So mono-substituted, maybe this might help. So mono-substituted, you're gonna get 5H. Di-substituted, you're gonna get 4H. If you're tri-substituted, your integration will be 3H. But just watch out, you might get symmetry. If you're like what is it, quaternary? I don't know what to call that. Tetra substituted. You have 2H, you know, so forth. You're probably not gonna see these. These aren't as common. You'll probably see more of these 2, 3. but then just remember like the locations and think about what you might see. So I would really use integration for these. Another cool hint, if you have para substituted, you have symmetry here. So para substituted often just looks like it's just a little more advanced, but you'll see like a mirror split images and you'll see like two peaks like this. That's probably para substituted. It's called Dock effect. I don't think you need to know that, but that's a cute indication that you have a para substituted. Ortho and meta, you're just gonna have to play around. Meta has some interesting long-range complex stuff, but you don't need to know that. With TLC, what you need to know with TLC is versus IR. I guess like IR tells you functional groups. This can tell you, did I get the product I wanted? Okay, and then TLC will tell you purity of your product. And I guess completion of reaction. So IR and TLC are a little bit different. TLC will tell you your purity. So do I have a mixture of my product? Is it 100% pure? Do I still have reactants left over? Present. So that's the question to ask. TLC is a diagnostic, I guess, monitoring method. IR is more of you can determine functional groups. You can kind of determine what more structure determination like NMR. TLC is nothing. So TLC will tell you nothing about your structure. It will tell you about polarity, right? But there's a huge focus on polarity for some reason. But the thing is, in this class, we don't care about polarity, and it's like as a I guess we don't care about it as chromatography as much. All we care about is, do I see 2 spots or do I see 1, 2 or 1? And then for IR, what we are focusing on is functional groups. So like, what functional groups are present? Do I see ester? Also, you should know the ranges for these. These are around like, so I think this is around 1760, a little bit higher. Things like amines are lower, 1680 maybe. These are just numbers I'm guessing, like inverse centimeters. So like you should just note those. Like so, something else is inductive effect. On IR, inductive effect shifts leftwards. That's why esters, because of the oxygen, like it's kind of like electron donating quality, that will cause, the inductive effect will cause it to shift leftwards towards 4000. And then for amines, the resonance, so resonance will shift, they're kind of counter effects, it will shift it rightwards. Resonance also like conjugation. So conjugation is another big thing you can notice from IR. I think hopefully this helps you with this part. Yeah, and he gives you the chemical shift ranges. So I don't think you need to sit down and memorize it, but you should know usually esters are higher up. Ketones, aldehyde, somewhere in the middle. Aldehyde will have a special sp2 peak around like 27, 200, 2007, 2820. 2820. Let me write that down. So aldehydes, you'll see the sp2 around 2720, 2820, and you'll see like 17, I think it's like 1715, 1720, I don't remember. But ketones also show up around there for these, and you won't see these for that. Okay, so that's another thing. So usually just esters, then around ketones, amides. I mean ketones, aldehydes. Then you have around about like amides, and then conjugation just goes down. So you just know that. And then I will talk about these different things. Okay, so let's see. I'm gonna try to do this. I will try to put this in here. So let me, actually, I'm gonna screenshot this. And then I wanna answer these on the whiteboard. I'm gonna share my whole screen because this is not working well. Okay, so I'm gonna share this so you can see here's the reduction, vanillin acetate with NaBH4, and then here, this one. Okay, I'm gonna try to do this screenshot stuff quickly to not waste time. Okay, so you'll see here, synthesis of nylon and bakelite, synthesis of chalcone. My numbering scheme is off because it used to be the iodosalicylate reaction last, and we didn't do the bakelite lab, so that's why I always associate chalcone with 5. When it's not, I don't think it's 5, I think it was your experiment 7. And Robinson, I think of as 7 when it should be 8 for you guys. Okay, so we'll go through these quickly. I assume also I'm gonna let me just screen share here. Sorry, that's my other homework. I didn't want to need to share that. Okay, so here, just focus on these 4 experiments, and then I think you can see the first 2 exam pages, the study guide, which I just was talking about in screen sharing. The final from, okay, yeah, this is a final from last year or 2 years ago because it's fall 2018. And then you can go through those. I think these are the post-lab question answers. So I really encourage you to like re-look at these. I remember this one was a cross-linking question. There are some questions. I'm sorry I'm jumping around, but there are some questions like you see this cross-linking. It's kind of like arbitrary and out of the blue, like, oh, how does it really relate to big picture? Don't focus on those like extraneous kind of like questions as much. Focus more on the ones that are specifically like for relate directly to reactions you've done. So for instance, this one is definitely a good one. Like it's an aldol mechanism. You need to practice this. You need to know what mixed aldol versus self-aldol, crossed aldol, that stuff. This one was a kind of enamines. Like you don't really talk about it. It's not in the lab manual. So like don't focus on this too much. Yeah, you should know how hybridization impacts things. So like sp2, sp3, know the effect of resonance, know the effect of inductive effect, know the effect of bond strengths, bond angles, bond strengths. That's something to know for like a conceptual kind of, those type of questions, because you saw that in the practice past final and then probably in the midterm. You can see here, this one is also really good reaction to try out. The Robinson, I would even encourage you just add even more stuff on here, this product, and then ask a friend to do the retro synthesis, whatever it's called, go backwards, because you need to go forwards, but you need to also know what bonds form and break. I'm gonna come back to this. Yeah, and you should know like what causes things to be more stable: conjugation, resonance, inductive effect, sp2, those like hybridization, p character. Yeah, definitely study that. This is the first 2 pages of your exam. I would even print this out and like review this. It's open note, open lab manual, open old labs. That means don't like communicate with other people. Use a calculator, have it next to you. Personally, like I remember I needed to use a calculator. I just use I use a TI 36X Pro, but it doesn't matter what calculator you use. Just needs to be able to do simple math. Also, relevant data tables, NMR shifts are blah 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 appended to this end of this exam PDF. I don't know if it's on this one. Oh yeah, cool. Then print this out, have it next to you. You want to have the molar masses. Like this is very important, especially when you do elemental analysis, because elemental analysis is another aspect of structure determination. That's the thing where you do like, oh, what percent of C do I have? What percent of H? What percent of O? So that was in your first lab experiment. But that with like empirical and molecular formula is something that also kind of gets lumped in with NMR and like IR and structure determination. So that's something that you should still review. So like review mass spec maybe as well. You can see here are different chemical shifts. I would not memorize this, but like just the general things. Like I think I told you earlier, right here, that if you this is the HNMR. But if you saw a quaternary carbon, this is what I was meaning. Like if you see tiny blip like this, that's probably a quaternary carbon. And this one is probably in the C double bond O range, carbonyl. But if you see a quaternary carbon here, that likely means that you have some sort of like X looking thing. That's why I call it a cross or X looking thing. And then you have, they're all substituted, no protons here. You'll have alkane kind of quaternary carbon. So like things like that, just pay attention to. Quaternary carbon is really small, so don't ignore that and ignore the solvent peak. You can see here peak intensities. Here's different functional groups. Once again, I wouldn't focus on anything under the fingerprint region. We do not care about that. This is something you should definitely know. When you see alcohols, you always think of a broad peak, but the alcohol can be a sharp peak. It does not have to be like fat and broad. I think it has to do with OH bonding. So this one has OH bonding. The sharp one is no OH bonding. It's like called free. It doesn't intermolecularly hydrogen bond intermolecularly, I think, or something like that. I don't remember the specifics. Just amine, amine, these are sometimes hard to distinguish. But amine, you should be able to tell the other peak from it. It also has a partial double bond character. And because of this, that's why it shifts right. And it's lower. You know that the C double bond O peak is lower than like an ester ketone. Yeah, you can see this is the alcohol part, and this part are probably the only parts of IR I care about. You can see it's lower, and the reason why is amides have this like special double bond character as well, and it's just resonance. So like you can just think of it as resonance, and because of that, this bond right here, single bond, is actually a little bit shorter. That's what it is. So like the CN bond, a little bit shorter, so it displays kind of partial double bond character. You're gonna learn about this more in biochem when you do like peptides and stuff. But I thought that was pretty interesting, so that's why it's lower. But you can see that something like an ester is much higher in the shift, and that's because, so if you see amide, it's because of resonance. If you see the ester, I mean, ester can be conjugated too. That means it'll go lower than what you expect. But like, yeah, this is because of inductive effect. I just know this from like my structure determination class. I'm taking CHEM242. So if you really like the stuff, you can take that. I'm taking it with Dr. Falvey. Yes, and then you can see aldehyde and ketones low different and carboxylic acid. I would just focus on these groups. I don't really care about that. You're not going to see anhydrides and acid chlorides much. You didn't even learn much about that. Okay. I think that helped. What is this? The indentations on dice to indicate the value of each side are called pips. 5 pip pattern on an X die is called quincunx. Okay, I have no clue what this is. Yeah, that is not useful information. I just find this kind of cute though. Yeah, also Dr. Freeman uses soap bar. So if you need to do degrees of unsaturation or IHD, soap bar, DOU, whatever, these are all the same thing. So that just tells you how much unsaturation you have, like the rings and the bonds. You should just know how to do that probably. Okay, isotopic abundances. Okay, so this is telling you that in mass spec, the M plus peak, this might be helpful information. It might be a little bit more, but this is 3:1. So it's the M plus peak to the M plus 2 peak. So you can see this one is 1:1 and this is 3:1. And the reason why is because of its natural abundance in the atmosphere. So if you actually see two bromines, then you see a 1 to 2 to 1. I think this is cool. But that's because you have an M plus, M plus plus 2, and you have an M plus plus 4. And how you do this is pretend you have x plus 1, x plus 1. This just follows like foiling, so then you get x squared plus 2x plus 1, right? So then this is y is 1. The coefficient here is 2, and this one is 1. So the middle one, you can have two combinations. You can have this x and this x, or this x and this x. That's why you have a 1, 2, 1 peak. For this one, if you do the same thing, 3x plus 1, 3x plus 1, then you get 9x squared plus 6x plus 1. So then you get a 9 to 3 to 1 ratio. Members M plus to M plus 2 to M plus plus 4. And the reason why it's the 2 by 2s is because this is 35 and 37. So then for instance, bromine, actually, you'll see 79 to M plus, sorry, it's not 79, you double it because this is 2 bromines. So then you would get, I have a calculator next to me, 79 times 2, so you get 158 to 162. Actually, okay, this is not the most accurate. Anyways, that's not okay. Anyhow, like because I'm not going to even explain that because your molecular ion peak is actually not going to be equal to that. It's equal to your total molecular mass. Sorry. So, but anyhow, you get the M plus to M plus 2 to M plus 4. And it's similar to the dye idea, but probability, but you don't need to know that. And so if you had the bromine and a chlorine, what will you get? You can just do x plus 1 times 3x plus 1. You can figure it out. 3x squared plus 4x plus 1, so it's 3 to 4 to 1. So you can just play with this all day long if you want to. I don't think it's that relevant, but I've seen before something like that. So like, yeah, multiple choice answers can be selected and blah, 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 just follow these directions. Molecular formula should be entered as blah, blah, blah. So I guess if it's CH4, you just say CH4, not C1H4. Numerical answers have a tolerance of plus or minus 0.04. That means that you should not be rounding throughout your calculations. This means that you need to be precise and carry it in your calculator. Do not round throughout. And this doesn't matter if you use like Excel or like sometimes I use Excel as a calculator because it saves everything on there, or you use like your calculator, graphing calculator, scientific calculator. Just don't round it. You need to use the exact values. Do not enter units. So do not enter units, just follow that. Make sure you read instructions because he's giving it to you here. Some questions have multiple correct answers. That means you need to choose all the correct answers to receive full credit. So like Dr. Freeman doesn't give a lot of partial credit. Just that has been even traditionally on exams. So my biggest tip is you need to read carefully. It's very unfortunate, like if you just do a whole problem right and then you forget the 4 hydrides per like 1 mole NaBH4. I've done this before, that's why I use this as an example. So things like that, you should just definitely read careful, get used to the format, think through it, don't panic. Like panic is not good, so don't do that. Yeah, and then you have that final from last year right here. Or not, sorry, not last year, 2 years ago. It used to look like this, and you put all the answers in the front, and then the TAs grade us quickly. So it's pretty much the same like format. Yeah, so like here you need to just be smart. This is an NMR problem. You usually start off with NMR IR problems, the mass spec. This one I would not pay attention to that much because this sounds like more of an experimental procedure that I feel like that'd be on a lab practical. There's no lab practical. There's also another question here. Like this one's probably deals with electrophilic aromatic substitution. It says ionization of salicylate. Just remember, it used to be experiments 4 to 8, but or 5 to 8, sorry, whatever it is, but the 8 was iodination. So iodination, sorry. But basically, if you see any of these old questions that you already got tested on midterm, so like don't pay attention to that. The one experiment that is not shown, okay, so Chalcone was in the past. Yes, it was on the final. Robinson was, and the Nylon was. But the problems that are not are backawate and your reduction. That might be on a past midterm actually of vanillin acetate. That might be on a past midterm if he gave you any examples of past midterms. So go look and study these because they're not on this practice final. I would not just only do this practice final and feel like I call it a day. Okay, I don't want to make this video way too long. So let's go back to the whiteboard. Okay, so what kind of functional groups does NABH4 reduce well? Okay, I'm just gonna tell you honestly, I don't remember all these. I might not know the answers for all of these, but I'm gonna try to go through this quick. So, okay, so what type of, I'm gonna use okay, so what kind of functional groups does sodium borohydride reduce well? So from the past, when I think I just this long ago, it's also in your lab manual. It's only ketones and aldehydes. I think maybe acid quartz. I know, but don't even worry about that. It's only ketones and aldehydes for this purpose of this class. What does lithium alumina hydride reduce well? Okay, so it will reduce ketones, aldehydes. It will also reduce esters. It will reduce pretty much everything. Amides, anhydrides, carboxylic acids. This one's a question, but I think it is. Okay, but I can't remember. Some professors I think say yes and some don't. I wouldn't worry about it, but basically it does do esters and amides as well. So that's what you want to know. NABH4 is a basic reagent. As stated above, basic reagents or reactions. Actually, sorry, I'm gonna bring up synthesis of vinyl acetate here. You can, or sorry, that's synthesis. We want the reduction. My mistake. Oh, also, yeah, there was mixed melting point analysis to tell purity. I forgot about that. I wouldn't worry about that. Okay, so here you will reduce vanillin acetate. Okay, so this experiment, what is the main thing that happened? There is this arbitrary big molecule. We do not care about the whole molecule. All we care about is this aldehyde. So what is the functional group that's reacting? That's what you should ask. What functional group? For any reaction, you need to know this. Groups are reacting. I would even circle it or highlight it. Like write it on your paper. I guess it's online, so you can't really draw online. So like write maybe iPad or whatever you use. I don't know. But like basically aldehyde is turning into an alcohol. And it's not even just any alcohol, it's a primary alcohol because you're going all the way. You see also on this molecule, you have an ester. But you see the ester is intact. It's because NABH4 does not reduce esters, but lithium aluminum hydride does. So you need to know the difference between these two. Its answers to the questions are here. You can see lithium aluminum hydride and sodium borohydride of the two lithium-based reagents is much stronger. It can reduce esters and amides in addition to aldehydes and ketones, which is what I just mentioned. Sodium borohydride is better for just ketones and aldehydes. We don't need something too strong of a reducing agent. However, blah, blah, blah. Oh, this is an important sentence. If this ever gets tested, higher reactivity of aluminum hydride is due to the weakness of the aluminum hydride bond when compared to the borohydride bond. So sodium borohydride looks like this. Sodium, right? So Na plus, this is the counter ion, Li plus, whoops, Al, H, minus. So it's saying that this bond is weaker than the sodium borohydride bond, stronger. How reactive it is based on the bond strength. So because this is weaker, it's more likely to donate that H minus. In the mechanism, never draw H minus. Just you need to draw it just like this would go to, like, you know, something like that. Kick this up, like that's a ketone. Sorry. Yeah. So basically, yeah, you just draw it like this. Hopefully that helped. It answered that conceptual question there, in case that happens. You can see reduction occurs via a concerted hydride transfer from the hydride containing an anion to the carbonyl group, C double bond O. So right here you can see this reaction. That's how you draw it. Do not draw H minus. This is how you draw it. This BH bond just going up here, and don't draw a dangling B here. That's not how it works. Just draw it like this. I would even put this on your cheat sheet or study sheet. In reality, the product is complicated. Once the hydride occurs, the boron will stay on the oxygen until protonation occurs. You do not need to know this, but that's why it's more complicated. Sodium borohydride is ideal because it is a fairly stable hydride source and is tolerant of protic solvents like alcohols, whereas lithium aluminum hydride is highly reactive and it's going to react violently with alcohols and waters. That's similar to the Grignard lab. You cannot dump like water. You can't put Grignard in water because you're gonna destroy it. It's gonna do an acid-base reaction. I think that answers your next question actually. So you can see here, NaBH4 is a basic reagent. As stated above, basic reactions tend to be neutralized with acid. However, there's a danger in neutralizing this acid reaction with acid. What is it? I think the answer, is because if you have NaBH4 remaining, it can just do acid-base reaction. And you could neutralize that H minus, because if you think about H minus, its conjugate acid pK is around 60, so it's very basic. You do not want to just dump acid in very basic. It's similar to the Grignard lab. It could be a little reactive. I don't know exactly because I'm not in the lab myself doing this. If the NaBH4 is not acidified, how is it destroyed, since we do not want to dispose of this in the waste? I'm actually not 100% sure. I know this was asked in my office hours, and unfortunately, I'm not 100% sure for that. Sodium borohydride will react with alcohols at slow rate. It will absorb water from the atmosphere. That's why we put in a desiccator. So desiccator is that like cute little seal container. It's like a little vacuum thing. It's kind of cute. So it will like absorb ambient moisture, similar to like when you have silica gel packs in like, you know, the food containers or whatever to keep it dry. So you use, for these reasons, you use excess of this borohydride. That causes it to be slower. It's not 100% effective. Yeah, so this is actually the most important thing you need to know. I've made this mistake where I did a whole calculation right and I forgot the 4 moles of hydride. So some people write 1 mole of NaBH4 can, react with 4 moles of ketone. Some people will write, I do it this way, 1 mole of H minus reacts with 1 mole of ketone. and that 1 mole of H minus, sorry, there should be a minus. I'm sorry, 4 moles of H minus and 1 mole of NaBH4. It's the same thing. So you just need to know conversion factor. I hope that helps. I don't want to make this too long. What does it say here? I think pale viscous oil. You get the IR. Unfortunately, is not as fragrant. I remember that sentence. I think that what you're doing, you dry the ether. So the sodium sulfate actually just dries, gets rid of any remaining water. I think you also use anhydrous ether, or doesn't matter. It can be hydrous or not hydrous. Yeah, so unfortunately, I don't know the answer to this. I would just ask Dr. Freeman. How, if it's not acidified, how is it destroyed? Yeah, I don't know. Sorry. Why is it important to use the excess of NaBH4? This was answered just now as saying because we don't want it to be absorbing water and we want to make it slower and less reactive. If it's too reactive, that's going to be an issue. The stoichiometry of NaBH4 is atypical. Yes, so you just need to know it generates 1 mole of NaBH4 can generate 4 moles of equivalent hydride. Chemists monitor reactions. How can TLC be used to monitor the progress of a reaction? So I think this one might, like, instead of just refluxing or stirring forever, TLC can be used because you can take the reaction mixture, just dip it, spot it. So you can just spot reaction mixture, effluent, whatever it's called, you spot it, right? And then you can just set this aside while your reflux is still going on. In the lab, you're doing a TLC, and then you can see, oh, I'm gonna put my pure reactant, and here I will put my reaction mixture. And then later, I should just see, this is what I should see. I might see a mixture, right? This is a product, 2 dots. No, it's not good. So then after, like, you know, long time and complete, when you complete things, maybe you'll get like just one, that's one dot pure. So then it's 100% successful. So that's what you'll do. Yeah, it's pretty repetitive, some of these things. Hopefully that was helpful. This is not good. Don't know why things are on here. This is bothering me. Yeah, so I don't know how to just get rid of. Yeah, so I'm gonna just move these up. Yeah. Okay. So then we move on to your synthesis. Sorry, this is like zooming in and out. I'm trying to get rid of. Okay, so then we go to your synthesis of nylon and bakelite. What is the role of the base in the synthesis of nylon? Okay, so your question here, what is the role of the base in the synthesis of nylon? Let's go back to manual. So yeah, just know how to do theoretical unit stuff. IR. Okay, synthesis of nylon and bakelite. You're synthesizing polymer of nylon. You're creating nylon 610. What does the 610 means? what the 610 means is it's at 6 and 10 position or something. You don't need to know that. I would focus, I think one of the fall 2018 questions asks about the intermediate in this reaction. You should just know the mechanism. What you are doing is you take an amine, right? The functional groups that are reacting is your acid chloride and your amine. And you know that acid chlorides are very reactive. Amine, you're going to do a nucleophilic attack to get an amide. So what happens is you attack this, then this is a nucleophile. This acts as your electrophile. Most things are electrophiles and nucleophiles. You create a tetrahedral intermediate. Then you have a good leaving group, chlorine. You kick it off. You have this like positive charge right here. I know there's two positive charges here, just ignore it. Like sometimes that happens. You have a base, and then it deprotonates this. And the important thing to know here is, what if I had different types of amines? You can't really have different types of acid chlorides, but with amines you can. You can have tertiary, so this is tertiary amine, right? You can have secondary amines. You can have primary amines. So you need to notice that here, because you do a deprotonation step here, this is also very relevant for when you do condensation and the alkyl condensation. Because you deprotonate, you cannot deprotonate if you have no hydrogens present. So all of these have lone pairs, right? So these will work, yes. Tertiaries will not work. So like because there's no H you can deprotonate. So right here, you should just notice like you can only react just primary and secondary amines. So this is actually primary, secondary. Or ammonia, like NH3 will also work. Yeah. So hopefully that helps, but ammonium doesn't really make sense because there's no chain coming off of it, hydrocarbon chain. So like, what is your polymerization? So yeah, so hopefully that helps. And then you can see what is the role of the base right here. So NaOH is actually functions as a base. Sorry, I'm a little tired. So right here, what is the role of the base in the synthesis of nylon? The base deprotonates, I think. Let me double check. Yeah, your base right here deprotonates that group. NH2 plus group of amide. Yeah, so hopefully that helps. And you can see right here. All right. Yeah, so then you keep nylon as copolymer since it's made of two different monomers. So that's the 1 mole of, just remember this, 1 mole of HCl is formed for every mole of amide bonds that are formed. So there's a byproduct of this reaction. That's what it's saying. You're getting HCl. Where does this HCl come from? So your HCl actually comes from when you drop this off, Cl minus. You also have H plus in solution. Let's just say that's why you have HCl. Yeah, this is just an acid-base reaction, so that's why you're getting HCl. You get kickoff of Cl each time. And you also pick up a H, so like I guess you could just say like Cl minus comes in, picks up a H, and becomes HCl. And it says by some base, deprotonation of ammonium by some base creates a neutral amide. So like that's the role of the base. It's a condensation polymerization. Implies the loss of a small molecule. It may not be water, in this case it's HCl. So it's a condensation reaction. So I guess right here you can say what helps determine which solvents the react. Okay, so that's a good question too. And also your HCl helps neutralize. It's kind of like the counter ion base. So like your HCl is byproduct. Sorry, this video might be a little long. Okay, so what helps determine which solvents the reactants are soluble in for the synthesis of nylon? So this is what I draw. So what you want to know here is you have an upper layer, and you have a lower layer. They are immiscible. So what is going on here is you have a upper like hexane layer. So it's a hexane. And if you remember from Orga 1, sorry, Orga 1 lab coming back, hexane layer is organic layer, and you have a lower layer. This is your aqueous or water layer. It's your aqueous. So you can see that right here is aqueous. This is organic. So it has so the upper layer has subacoyl chloride, and your lower layer has your 1,6-hexane diamine, which is your amine, and you have NaOH in the bottom. Okay, the reason why this is real easy. The reason why NaOH is in the aqueous layer is because sodium hydroxide is poor. No, it's Na plus, OH minus. Yeah, it's poor. So obviously it's going to be in the aqueous layer. So ion. And then your subacoyl chloride is on the top. I'm not 100% sure if you can just switch the hexane diamine and the subacoyl chloride. Maybe amines are just more poor. I don't know. They're just in different solutions, different layers because they're immiscible. And you want a solution interface for this reaction because it's a polymerization reaction. And you're gonna take, so what you do is you're gonna remove this layer with forceps. Sorry, these are my forceps. When you remove it, you're gonna start getting like a thin film, like a stringy thing. And then maybe you'll take this and wrap it around like a test tube. Yeah. So you're trying to take a long layer string of the nylon. Like you can think of nylon as like strings. Yeah, and then you don't want agitation. You want so the reason why it's immiscible, you want these two interfaces because you don't want all of it to react at once. That makes no sense. You're reacting at a surface, then you can start removing the surface, and then it's gonna start decreasing the both layers levels, and then you're removing everything. It's kind of like taking like like a hat, and then you're taking like these like tissues out. You take like a bunch of tissues, like the magician takes like a bunch of them out. You keep pulling it out, that kind of thing. So that's what's going on here. And then the second one is like the backlight lab. Okay. So that's there for you. Okay, so let's go back to backlight lab. It's the large number. N is just the number of times you do this. Okay, I did not know TAs can give you a bonus point if you showed them a strand of nylon that is 5 feet or longer. That's weird. Also just note that you have a 60% weight volume of 1,6-hexadiamine in water. That means for every gram of a solution, 0.6 grams is 1.6 hexadiamine, and density of solutions 0.93 grams per liter. Separately dissolve this, and then you see the density is 1.2 grams per milliliter of subacoyl chloride in 10 milliliters of hexane. So you just need to know. Okay, so you just need to know this is very important information. 60% weight per weight means there's 0.6 grams per 1 gram of solution. and it tells you the density of solution is 0.93 grams per 1 milliliter. That means you can get the number of milliliters. I'm sorry, I accidentally flipped this upside down. You probably realized. Okay, so then you can get 0.93 grams solution per 1 milliliter. So then you can get grams per milliliter solution for subaqueous, or sorry, not 1,6-hexanediamine. And this is important, you need to know how to do this math. As in this one, you can see the subaqueous chloride. You dissolve 0.45 grams, so that in 10 milliliters of hexane, and then it tells you that the density 0.4 milliliters. It's the same thing as 0.4 milliliters. The density is whatever, so that's how they got 0.45. Okay, yeah, you just need to know how to do that math. Synthesis of bakelite. Okay, so saying it's another polymer. Blah, blah, blah. It's a reaction of phenol and formaldehyde under acidic conditions. Remember, it's under acidic, not basic conditions. CH2 bridges. So you can see this is where actually the formaldehyde used to be. So the formaldehyde, this piece, are the ones that are joining everything. You can see here. So they're in the ortho para positions, and you can see this like just interweb created. Remember it's ortho para because OH of phenyl, OH is electron donating group. So, and it's activator, and that's why you're gonna get OP director. So that's kind of what you just need to know. Formalin, this is the same thing. You just need to know the mass per water, mass, like the mass volume. Weight, just need to know this. I'm not gonna go through this right now because I think I'm losing my voice for some reason. Sorry, I'm losing my voice. And I don't want to lose my voice. It's kind of weird. Okay, so why does it result in ortho para to the OH? Phenyl, OH is electron donating group. In the synthesis of bakelite, how is formaldehyde converted to bridging CH2? So this is mechanism. Also right here, for both of these, remember the weight by weight or weight by volume percents. And you need to know how to use densities or concentrations in your math. You just need to know how to use these. Concentration comes first if you have it, which is either of these, then you can use density as a second one. If you have these, this is priority, then density comes next. Yeah, so I hope that like helped. How do you react this? So the mechanism is just, you have phenyl, two phenols, and you have a H, and then you react this. So this is electron donating. So I can choose O or P positions. I'm not going to draw the resonance structures, but I hope this helps. Okay, so just review your lab manual because you've done this before. Let me double check. So you are doing this in acidic conditions. Okay, so if you're doing this in acidic conditions, that means that instead of doing this first, you don't want negative charges. So if I do that, I'm gonna get a negative charge. So what I just need to do is protonate first. You protonate the carbonyl first when you have this in you protonate this first in acidic conditions. Then I attack this. I'm gonna get this. Yeah, I always need to count. So this is connected to this. So that's connected to this. And then that's connected to OH. So that's what I get. And then I'm just going to show it for pair position, but the ortho is probably the same. And then you have two H's, so it's primary alcohol. Now, and then what you need to do is you protonate this, HCl. Sorry, my mechanisms are kind of messy. You get a positive charge here. So then you kick this off. So then what happens here is you get, I always end up drawing bigger. So when you kick that off, you get a positive charge right there. I don't remember if it's okay to do SN1 or SN2. I hate SN1, SN2, E1, E2 from organic 1. Let me pause right there. Double check this, and you are going to get a positive, primary carbocation. But you just need to remember this actually occurs. Why we have it is unstable. It's actually primary benzoic. So it's fine. And then once you have that, then you take your other, this is your new electrophile. So this was actually your electrophile. So I think another tip I have for you is you can ID your nucleophile and electrophile. I'm sorry that this is very disorganized. Take your other one. Where do I want to type this? Doesn't really matter. I could do it the ortho position. Let me show that. Then we get this OH up here. This is now connected to this guy. And this guy is connected to OH. Yeah. So then I'm finished. You can do it between ortho pair positions and whatever. So I kind of showed it to you. This is a polymerization reaction. We don't have to keep going on. Okay, so I'm gonna just pause right here in case you want to take a screenshot. Okay, so then shell cone. I'm not gonna go into the other stuff too much. Okay, shell cone was the mechanism of the reaction. It's an aldol condensation, addition, condensation. In this case, we're doing condensation. So condensation is when you get an alpha beta unsaturated system. Sorry, that's like that. Or you can, so this is aldol addition, and this is a condensation. That's when you have to do elimination. What factors lead to favor the formation of one major product? That's a good question. So then we can go back to here, blah, blah, blah. Okay, so you did the mechanism there. And then here, alpha beta unsaturated carbonyl compound. Okay, so this is a base catalyzed aldol condensation. Remember, there's acid catalyzed and base catalyzed. They're a little bit different. You need to know that. So they give you a base catalyzed right here, but then you need to know how to do the acid catalyzed as well. There are only positive charges. Base has only negative. This is like, I think the biggest thing I have emphasized in office hours. We see people keep doing this all the time. Also, remember it says E1CB. E1CB mechanisms are unusable. That means that your OH leaves. And so I'm gonna just give you a reference for this because I know this can be confusing. So E1CB mechanism. So you should just look at this. I know this is like I know there was misleading, but there is a E1, there's an E2, and there's an E1CB. E1CB has 2 steps. It's not in, it's like E1, it has 2 steps. However, there is an intermediate like right here. And then you can just read this. I think like this might be helpful. So I'm gonna screenshot this. I'm having a mess right now. I'm gonna just no. Okay, so let me screenshot this. And then I will put this into here. So just remember E1CV here. That's for also Robinson. You can look at this. What factors lead to favor formation of one major product? It's a good question. Okay, I'm gonna just, yeah. So then you can see here, you can have 4 different products. So you can actually have, I think it's 2 to the n number of products you can get, because you can do self-aldyls, and you have like 2 mixed aldyls in this case. But then you need to, I'm going to put more focus on this because I think this is a main focus on the past exam, and then you can study. Just remember right here, there's alpha protons. This is symmetric. So you can only form, for this one, you only have one type of nucleophile, or enoate, in a basic condition. It's called enoate in basic. And in acidic, it's called enol. So enol looks like this. Enoate, and then this nucleophilic right here. Enoate is just okay, I'm not drawing this right. So enoate is just this. You have a negative charge there. Okay, so there's one nucleophile and one electrophile possible. You'll always have electrophile possible because you have a carbonyl. Right here is also symmetric. So same thing. But remember, what if you have something like this? Sorry, I accidentally drew too many. If you have something like this, then you have this is a torpedo, so you have no alpha protons on this side. Then you have to use the other one. That's how we can favor one product. We can just have like only have one spot for the position for the alpha protons, and we can kind of target what we want selectively. Here you can see there's the H here and the phenyl, and that's why we force this one to be the electrophile. We can choose reactants that are capable of reacting in only one productive way. So this is what he's saying. Right here, there's a phenyl here, and we have just this group. So we know this one, acetophenone, is going to be the nucleophile, and this is going to be an electrophile, or the target. And you create an alpha beta unsaturated system. So that used to come from, before it was like this OH, but now it's not. It is just this alpha beta unsaturated system. Another key thing to note, hopefully that's helpful. Another key thing you need to note is that you can end up, if you have a situation where you have something like this, and you have one alpha proton available, you cannot do, and this is for your enoate, you cannot do condensation. You can do addition, but you cannot do condensation. The reason for this is because when you do condensation, so let's pretend that I had this, it's my product. This is shotgun, but like I'm gonna just pretend that I had this, right? So I had added to acetophenone this group, then you're gonna end up having this group right here, because remember this was your nucleophile that attached to here. So this is your nucleophile that attached, maybe this is your nucleophile, right? Carbon, I would even count my carbons here, that attached to right here. So then what happens here is, in order to get this compound, so what we did here, sorry, I didn't draw this. reactor. To get this compound, you needed to do this hydrogen. You took this hydrogen and you take this with OH minus, then you dump it onto here. This is the E1CB, I think. Yeah. So then you dump it onto here. You create this enoate. Sorry, this is not like the best drawing. But then you dump it here, and then you kick this off. And so this is like E1CB. But right here, do we have any protons available? No protons. This is why you need to do condensation. Addition, you can do it anytime. You need, so your first proton was used to create enoate. First proton, create enoate. You deprotonate, and you create enoate, right? Okay, so then your second H, you need to do E1CB. Elimination to create alpha beta unsaturated system. But if you don't have a second H, you cannot do that. So you can only get addition product in that case. I hope that's clear. Okay, I've spent too much time on that, more than I wanted. You don't need to know all this. I remember like orange goop. One time I didn't, nobody got product when I TA'd last time. So I think I answered this just now. Alkyl condensations can be done both in acidic and basic conditions. You should be able to do both mechanisms. So I'm just going to show a little rough thing. So acidic, what's going to happen in acidic conditions? You have, let's say missiles and targets, whatever. So you get your enoate. Right? So you deprotonate the alpha proton. Sorry, I meant basic. This is the more obvious one. Sorry, so this is basic. You dump this, you get the enoate. And then if this was your target, then it's just electrophile. This is partial positives, and then that's the electrophile. But it's neutral. Remember, it's neutral because it's basic. So if you were in acidic conditions, what happens is you can't just dump the negative charge there. So acidic means what you do first is you protonate this. So I'm just going to use HCl as an example. Plus. Okay, so then you have an OH plus. Sorry, the recording's a little bit long. You can put it on 2 times speed. And so you have an OH plus, and then basically, then you can do the deprotonation because we don't want to just create negative charges, right? So we'll use something like water, deprotonate this. I'm going to show this, and then you get OH. You get an enol. So this is your enoate for basic conditions, and acidic, the nucleophile is enol. And then your target is not just this. You have, you will protonate it once again because we want a positive charge. So let's say we have this. This is your electrophile. And remember, this is resonance structures with this. So your electrophile is really just this. So I'm going to just highlight this for you for your Nucleophile is enol for acidic conditions. Basic conditions, your enoate is your nucleophile. For your basic condition, just a ketone, right? Because you're going to just attack it. For your acidic conditions, it's this. You have to protonate the carbonyl first, because if you don't, so like, why, a big question, why isn't it just this? Because if you attack something here, like a nucleophile, and then you kick this up, then you get an O- attached to a nucleophile, and this is not okay. No negative charges, no positive charges in basic conditions. That's why we get what we get here. I hope that helps, and then you can do that simple, like, the condensation addition thing. That said, the mechanism of the elimination of water to get enone or enal product differs under, so I think enal and enone, just know what those are, differs under acidic and basic conditions. Basic conditions favor E1CP, whereas acidic favors E1 or 2. How are these mechanisms different? So this is E1CB, sorry, that's CD, CB. This is E1 or E2. So in this case, you're just gonna do E1, E2, you're not using, so this one, your OH is leaving group. E1 in acidic conditions make good leaving group, so it become OH2 positive. Good leaving group. Yeah, and then you can just look at this diagram for more information. You see right here. I'm not going to explain this, but you can just do the mechanism out yourself. Okay, so then we're almost there. Robinson annuation. Okay. Oh, your enone is this. This guy is your enone. Sorry. So your enone is like that one alpha beta unsaturated system. So enone. This is a enolate. Your enal is I think enone is a ketone, and I think enal is aldehyde. So I'm not 100% sure. Anyways, I'm not going to talk about that. But basically, what you do, it has 3 parts. It has a Michael addition, then aldol condensation, then you have like a E1CB. So you do Michael addition, and you always create a 6-membered ring. Remember, this is E1CB, so please don't do this in one step like a E2. That's not right. Annuation ring making. You make 6-membered rings. Don't make 5-membered rings, 6-membered. Okay, you can just follow this reaction here. And remember the NaOH is catalytic. I hope that helps. Okay. So I think, why is dehydration favored at the end of the reaction? We'll just answer this last few questions. Dehydration you yield an enone, which is an alpha beta unsaturated system. It's just more sterically favored. OH is just, left over on there. I'm not 100% sure. I think it's just more favorable, like it's conjugated. Yeah. Remember, this makes 6-membered rings. And you're taking an enone, which is an alpha beta unsaturated system, plus enolate. Okay. Allows them to be mixed in one major. Okay, so then this is also the same as before. you force only have one alpha proton positions, or you create symmetric enones and enoids. Yeah, so I think that should be helpful. There was one last part I wanted to add, but I wanted to just show you an example of how to study the Robinson. I'm really losing my voice. This is not good. Sorry. I usually am not like this. But I'm gonna finish this video. So let me show an example. Let's pretend I'm creating this problem, just making it up, okay? This is self-symmetric. I mean, I don't know what this is. I just made it up. Okay, and let's make this problem even more trickier. Let's put like, ooh, let's do that. Yeah, let's put another. Actually, I don't want to do that. I don't know how it's gonna react. Let's just put another let's put like these like groups. Okay, so let's just, this looks very complicated, right? And then let's add we need an enone. So I'm gonna make one up. Okay, so let's say we have this enone right here. So this is like a enone. Ooh, let's make this even more tricky. That way I can't figure this out beforehand. Not the biggest fan of doing tricky problems. Okay, but basically what we can do here is, so we see an enone, so what do we get? So then what we just need to do is, one, create enone. So let's pretend we are in basic conditions. So I'll just put NaOH, H2O. Okay, so then there's an alpha proton here. This is symmetric, so we don't really have to worry much about anything. So OH minus, kick this off. Let's create an enone. It's gonna be pretty complicated. Ooh, whoops. I didn't mean to make it asymmetric. Okay, so here's our problem. So then once you create enone, I made this up on purpose because I don't know the answer to this. I just made this up on the spot. And then once you create enone, what do? We just need to then Michael addition, 1,4 addition. So then all you need to do is attack at this is self-nucleophile, so you'll attack at this position, the 4 position. You rotate the bond, swing it over like a hinge, kick this up, and then what we get here, oh, now we're attaching a ring, so this is gonna be more complicated. Okay, so what we need to just do is not freak out, don't panic. I remember when I took the class, I panicked. Let's just draw. Okay, so my tip is just keep one of them the same. I'm gonna keep this guy the same. Keep one of the reactants as the same, as similar as possible. Okay, I definitely broke the octave rule in this ring. Didn't mean to do that. Whoops. So this should actually look like, it doesn't really matter. looks like this. Okay, so then once we have this guy, it's just a practice in drawing. So then now this is connected to right here. And this is connected to 1, 2, 3, 4, 5. So then now I'm just going to draw a 6-membered ring. That was connected to right here. Doesn't matter. And then I choose this. I swung it over because this was connected to here. But then that was swung over. So then we have this. And then we have O kicked up. And then that's what I got. And then what we just need to do now is, I call it kind of like, you can have also more steps than, it depends on how you annotate things. So I would just recommend you annotate things. So you have OH, you kick this up, you reform. So I'm gonna just call this reform C double bond O carbonyl by hand. Make C double bond C into alkane. Okay, so then once you do that, then you get down here. I think you should also label. So if I did labeling, I can just tell you this is like 1, 2, 3. If I had 1, 2, 3, so it's like 4, 5, 6, 7. So then I see that 4 is connected to 5. So this was 5. 6, 4, and you see the 1, 4 bond was created. So this is 2, 1, and then 3. So it was 1, 4 bond. According to my notation, I could have called this AB. I don't like how I said 1, 4. It's just gonna make it confusing. But okay, so then once you do that, you're gonna just go down, draw this monstrous thing. Yeah, I don't think you'll see anything as difficult as this. Used water by using water. Pyranation. Okay, so now we have 2 ketones. You're going to realize 2 ketones, carbonyls or whatever. So what we just want to do is now we make an enoate again. 4, make enoate. But which enoate? So what we usually do is we will pick the other one. So because I first made this ring an enoate, I'm going to make this one an enoate this time. Just like, I call it ring around the rosy, you switch turns. I don't think that makes much sense. But so obviously it's not going to be this position, because if you do that, you'll have 1, 2, 3, 4, and it's not a 4-membered ring. You can't do that. It's not stable. So it's not going to be that. But then what about this? Then you have 1, 2, 3, 4, 5, 6. That's perfect. That is a perfect ring. I guess you could have used the other one, but in this case, we'll use this position as a rule of thumb. And then once you just do that, you just need an OH minus, deprotonate this. Then this is going to be complicated. So you make the other, I'm going to just say other ring. You make the other ring, whatever was on the enone originally, you make that into this. So, whoops. So it should look like that. This is just more complicated to draw and kind of tedious. Okay, that's kind of disgusting. than it being difficult. So then once you have this, all you need to do, I think the easiest method to form this ring is, it's going to form a 6-membered ring. So there's going to be another ring. So what we just need to do is connect this guy to this guy. Sorry, wrong one. This guy to this guy. So you're connecting this to this, those 2 dots. So what we just need to do is, so we'll take this and kick it up. I'm sorry, I skipped a step. I'll just quickly draw the Enoate. This is why I'm saying this is tedious. So then that's the Enoate. Then I'm gonna draw this very quickly. So I'm getting sick of this too. Okay, so then what we just do now is we take this guy and let's use orange or whatever this color is. We kick that up. So that means we're gonna take this guy. So I'm gonna count 2, 3, 4, 5, 6. So I'm gonna make a 6-membered ring. So we'll do 1, 2, 3, 4, 5, 6. And you know that this carbon is 6 right now. So then 6 is connected to 1. 6 is also connected to 5. It's connected to 4. So that means 6, 5, 4, 3, 2, 1, and 1 is connected to 6. There's our ring. And then we know that at 6, the O pops up. So we have a O popping up right here. Okay, I'm gonna just draw this in black to show this better. So this is the in black is the new formed ring. And there's a lot of rings here. So 3 and 4 are also 2 and 1 are also connected to a ring. So 3, 4, 2, 1, 3, 4. Oh yeah, so then this becomes even more complicated because you get a bridgehead. So I shouldn't have picked this. But anyhow, you get some crazy complicated structure. So like, I guess I solved this in the end, but like, just, yeah. And then all you need to do is protonate. Sorry, I came up with an example that was too difficult. So you're getting this, and then also I forgot to, the 2 position, you have O sticking up. And then you can see right here, there's the H, and that's gonna be the one we're gonna target. So then right here, we get an O, we get HO. So this is our addition product. I'm gonna just draw the bridgehead. Okay, so then what we just need to do now is take this H and do E1CB. You dump it on. Now you get an Enoate. Okay, I'm getting annoyed by like drawing this many times. So I'm gonna just okay, so we're gonna get this Enoate. I should have just copied and pasted from long ago. And then once we get the Enoate, we dump this, we kick this off. So we're doing a E1CB. So right here, I guess 5 protonate. the oxyanion to form OH alcohol, and then you get 6 form deprotonate to make enoate-ish, I guess. Step 1 of E1CB. This is part 1 of E1CB, and then part 2 of E1CB is 7 eliminate OH. So then right here, so then what you're gonna get in the end is you'll get this alkene. So this is alpha beta unsaturated system. And then once you get this, you just need to realize if you were going backwards, I'm going to give you one example of going backwards. But this is how you do this mechanism. Sorry, it's like very long. Feel free to screenshot this and show that. Yeah. So okay. So here's the mechanism, so you can feel free to screenshot that. I know this video is getting very long. Okay, so I'm gonna do one more example. So if you got something like this, right? This is my Robinson new weighted product. Oh, my voice feels a little better. Okay, so whoops, and there's, then how do you go backwards? So this was actually an example I did for my students when I TA'd the lab 2 years ago. So then basically what you just need to know is, what's the previous step before this? So what we just did was we used to have an OH here, right? So then we know that this bond and this OH, before it was an OH, was a carbonyl, right? So we are breaking this bond. So we just need to break this bond. So that's what we want to do. So we'll just swing over. So I'm going to just draw the rest of this with that bond swung over. So you know that this center was the electrophile. So this pink one was the electrophile. And that this yellow one was actually, sorry, not the yellow. Right, this center was actually the nucleophile. It was the enoate. So then that, because we know that, then we can go backwards to an intermediate. So it used to kind of look like this at some point, and then we made this guy an enoate. We made this guy an enoate, and this was our target, carbonyl target. So then what we just need to do is now, I can show this in like a 2-step quick, we figured this out. Okay, so then there are 2 bonds that formed the 6-membered ring. So to go backwards, you just need to identify 6-membered ring, which was the right one in this case, because all you need to do is find the alpha beta unsaturated system. Okay, so just find that. It's a quick trick, and then find wherever the condensation product was, the alkene, that used to be an alcohol, and that used to be a carbonyl, and that used to be for the, not the Michael product. So then once we have that, we then realize, oh, well, you want to locate the alpha positions of other ketone or carbonyl. So that's what I mean by flip-flop. So then we realize nothing's connected here, but this is connected here. So this is the other bond that was formed. So 2 bonds formed, and we were trying to figure out where they were. It was right here, and the earlier one I already circled. And so what we just need to do is break this guy, because you know this used to be enoate at some point. So this is one of the products, and this guy is another. Remember that the enoate targets, so this was actually the nucleophile this time, and this was the electrophile, but the electrophile was the enone. That means it tagged at the 1,4 position, at the 4 position. So that means you just need to draw alkene right there. So these were the 2 products, reactants that I used. And check, yes, it was right because I made up this problem, so I know it was right. And they match up with what I actually gave students. So perfect. Yeah. So that's how you do it retrospectively. I think that's enough information. This video is getting too long. I hope this really helped. Last minute tips I'm gonna write. I'm sorry my typing is gonna be a little loud because I know I just type loudly. Okay, so I'm gonna just give you last tips. And I have other things I have to get done. So you need to read carefully. This is just for me to use since I took this class a few years ago. I took it freshman year and I'm a senior now, so it's been a while. So you just need to, I remember the final and midterm were pretty difficult. You just need to read carefully. The format should be similar to midterm, so you're already familiar with it. 2, please locate, another tip, locate functional groups. You need to be able to locate functional groups that react. So like enone, like for instance, alkyl condensation is enone with a, I'm sorry, Robinson is an enone with a enoate. So you just need to know that. Write down mechanisms, and furthermore, you need to know if it's acidic or basic conditions. Also have next to you maybe like reagent tables, stoichiometry. So like just know like that 4-to-1 ratio of the hydrides, but everything else is usually, so it's usually 1-to-1. So hopefully that's helpful. 5, you need to so read carefully once again. Pace time, but don't panic. I remember I used to panic, I just guessed. Guessing comes last. Do not just guess for most of it. I think you can, if you sit down and actually think through it, you can solve it. Panic causes problems. Okay, and then another thing is just focus on, you can do NMR. Remember that you need to remember things from NMR, IR, mass spec, TLC. I never really saw TLC much, but like just know these things. Elemental analysis. Remember these were experiment like 0 materials, so that was the structure determination lab. So like just know things like that. Yeah, know the acid or base conditions. Count carbons or label them. And there are quick tricks that I showed you, especially with like the tertiary and secondary and primary amine for the nylon lab. And I also showed you for the alkyl condensation and addition that you can't do condensation if you don't have 2 protons. You need at least 2 or 3 protons. If you only have 1, then you only go to addition and that's it. It's similar to like when you do alcohols and you create it's similar to when you have like formaldehyde, you can create a primary alcohol, but then if you have like a primary alcohol, then I'm sorry, if you have just an aldehyde, like, okay, so yeah, that's just similar to if you have like this, then in the Grinder lab, you know, you can make OH, like that's It's a primary alcohol. No, I'm sorry. Yes. If you had a formaldehyde, you can make just this OH methyl OH. Yeah, and then if you had a ketone, you make this, like similar to that with amines. Only realize that with your like nylon lab, you can only do NH3, NH2, and H. But if you don't have an H, you can't do the deprotonation because that's in bold in the lab. Same thing with the Robinson and Shalcone. You just need to know if you have the two H's, you can do condensation. Only addition. And then I think we had one last tip I had. So read carefully. Units, be careful with units. When you're doing stoichiometry and that stuff. Count carefully. The biggest thing, everything is like a nucleophilic or electrophilic attack, so let the charges guide you. That's how I navigate orbit 2. 8. Each lab will pertain to one of the topics, so it's either going to be the structure determination or one of the 4 labs you had, so you need to ID what experiment the lab is talking about. I would do this actually as one of my first steps. Right here, this one. Yeah, do that as one of your first steps. And that's my last tips for you. Good luck on the exam. I think hopefully you'll do well and don't freak out. You can screenshot this if you want. That's it. I'm gonna really cut the video because I'm being tired and I have other things to do. Good luck on finals. Let me stop.